All right, so good afternoon and welcome back to the final session on wheel mobile robots. So I hope you have covered all the 8 weeks worth of lectures uh, until this point. So every week we have had some sample tutorial sessions where we would discuss uh, that particular week's worth content, and we would also solve some sample problems. So we have covered all 8 weeks worth content worth content during these tutorial sessions. And the purpose of this tutorial session today is to solve some doubts in general if, for any of these topics covering starting from week 1 all the way to week 8, and is also to review or just to briefly glance or quickly glance over the topics that we have covered from week 1 all the way to week 8. So I have prepared a lot of slides, maybe around 94 slides, but I won't go in detail through each of them because there are a lot of topics that we covered during this 8 weeks, of course. But this session is actually meant to refresh what or just to refresh or recollect all the topics that we have covered during this course. Yeah, so we'll get on with the session. So moving to week 1. So in week 1, we generally dealt with introduction of mobile robots. Like mobile robots could comprise of different solutions. Like the locomotive solutions could comprise of leg locomotion, wheel locomotion, maybe even track locomotion, underwater locomotion, aerial locomotion. So those comes under mobile robots. Everything comes under mobile robots. And we also came across a class of what we call as robotic manipulators, where its purpose is to manipulate objects around it. And from there, we have actually targeted to different kinds of locomotions, different types of locomotive solutions. And from there, we again further narrowed it down to wheeled mobile robots. Like from all the different kinds of solutions, we have narrowed it down to wheeled mobile robots. We have also covered its advantages, and where wheeled mobile robots would be more, suited. And then we would conclude week 1's lectures by defining these terms, what we call as degree of maneuverability of different configurations of wheeled mobile robots, and various types of wheels that we would use for different configurations of wheel mobile robots. So, in the earliest lectures, we have actually seen the definition of effectors, which is nothing but any robotic device that has an effect on this environment. And there are two classes of effectors, which are manipulators and locomotion devices. And manipulators' purpose is to manipulate the objects around robotic manipulators. And locomotion is its effect causes the motion of the effect itself. Motion causes its effect on the environment causes the motion of the effector itself. So such devices are called locomotive devices, right? And we have also seen the key differences between manipulators and mobile robots or locomotive devices. So what we see over here is a example of manipulators, and the other being mobile robot. So in this case, it's specifically this is actually a wheeled mobile robot. Right? So the most important difference is that the base link or the base of the manipulator will be fixed, right? So in that regard, the workspace of a manipulator will always be constrained or will always be limited. Whereas in the case of a mobile robot, the workspace is actually unlimited. It does not have any sort of constraints. It works on an unconstrained environment. And as a result, it need more sensors to perceive its environment. It also need additional sensors to avoid collision with obstacles. Right. So those were the key differences that we observe between manipulators and wheel mobile robots. And then we also since the course is about wheeled mobile robots, like from the differences between manipulators and mobile robots, we narrowed it down to mobile robots in general, we have also seen their capable advantages or their defining traits. Right, it's an automatic machine capable of locomotion. It's not fixed to a location because it can locate. It works on an unconstrained workspace, so it can roll, walk, fly, or swim. So these are the multiple possibilities or multiple solutions for locomotion. And they also are less structured. So in that regard, they need more sensors. Their operation is actually less structured than a typical robotic manipulator. And as a result, in order for them to perceive their environment, they need more sensors when compared with robotic manipulators. And we have also seen the fundamental problems that a mobile robot should address. It should be answering these questions about where am I, where the robot currently is, and where am I going, where should it be going, and how do I get there. So the fundamental problem that we should be solving for a mobile robot would be to address these questions. And then further, we also have seen various subsystems of a mobile robot, which is locomotion, basically how a robot moves through the environment. And as you know, we have multiple solutions for this problem. You can use wheels, you can use legs, you can also use aerial solutions, you can use underwater solutions, depending on the type of application that you are, employing this robot. And the other subsystem would be the second would be sensing, how the robot perceives its own information and, for what it sees from this environment. And also, basically, its reasoning capabilities, how the robot maps its data from the sensors into, executable actions that control, how the robot executes planned actions, and communication, how the robot communicates with the external operator. And then we have also seen the key issues in locomotion, which includes stability, right? Whether the number of contact points is stable, whether the center of gravity is within the polygon enclosed by all the contact points. Then the contact characteristics, area of contact, friction, all those things. And the type of environment, the structure, medium, all these aspects comes into picture. Yeah, and then we have also seen the different kinds of mobile robots, whether it is a wheeled mobile robot, which is what we are covering for this course. Then we also have tracked robots where they use, it's belt-driven tracks so that they can, navigate through very rough terrain. We also have legged solutions, which is, as you know, preferred by nature. It is what we observe in the nature, and even legged also has multiple solutions. We have biped locomotion, similar to how human beings walk. We have quadruped locomotion, similar to how most of the mammals locomote. And we also have, hexapod and octapod solutions, with six or more number of legs. And there are cases where we would combine, multiple, many of these solutions into one, which is called a hybrid solution. So the example what I've shown here is an uh, hybrid robot. Actually, it comprises of legs, anthropomorphic legs, and at the end of these legs, we have actuated wheels. So, like when the robot is moving through an engineered surface, a flat or a smooth surface, it can switch to wheel locomotion, which will be more efficient. And if the robot is going, outdoors in rough terrain, it can actually use its legs in order to, tackle the obstacles. So yeah, these are pretty much the different kinds of land-based mobile robot solutions. The keyword is land-based. And if it is not land-based, we have even further solutions. And if it is aerial, we have, aerial roads, aerial unmanned vehicles. And if the robot is operating within, underneath, underwater, we have underwater solutions, right? And what we have seen or what we have shown over here is strictly limited to land-based mobile robots. And yeah, now since we have given a general overview of different kinds of robots or different kinds of locomotive devices or mobile robots, we now deal into the mechanics of wheel mobile robots. And in mechanics, we first cover the topic of kinematics, actually, where we only study the motion of the robot or a rigid body without considering the forces or efforts that causes the motion. Right? We are only interested in position, velocity, and acceleration. And at this moment, we are not bothered on what causes this acceleration. The efforts that causes this acceleration. So that is strictly what we deal in kinematics. And again, we have also seen the definition of what a degree of freedom is. A degree of freedom is nothing but a minimum number of variables that is required to describe a system. And as you know, in case of a wheel mobile robot, the degree of freedom is three because you need three coordinates to define the position of a point of a rigid body as well as one orientational parameter to describe its configuration or its orientation. And for aerial and underwater robots, you need six coordinates, which are three positional coordinates and three orientational coordinates, right? So whatever we are dealing with this course, since we are only dealing with wheel mobile robots, the degree of freedom for wheel mobile robots is three, right? Then once we are into kinematics, we have also seen the frame assignments. Basically there are two frames of interest. One is what I am drawing here is the inertial frame that is always fixed with respect to an inertial frame of reference. So I'll call this as xi and yi, the respective axes of the inertial frame of reference. And I'm also depicting the chassis of the mobile robot, right? And I also attach a frame maybe at the centroid of the mobile robot. So this frame, what we call as body fixed frame, is always going to be fixed onto the mobile robot or onto the chassis of the mobile robot. And I'll label its axes as XB and YB, right? And we will also define the velocity coordinates along XB axis as U, and along YB axis it will be V, and the angular velocity along the Z axis, ZB axis would be R, right? This is angular velocity. And the corresponding velocities along XI axis would be X dot, and corresponding velocity along Y dot would be, Y axis would be Y dot. And the angular velocity along the Z axis of the ith frame would be psi dot, right? And you also define the orientation of this body fixed frame XP with respect to the inertial frame of reference xi using this angular displacement parameter called psi. And if you are given this psi, you also know how to map this coordinates x dot, y dot, and psi dot, right? We'll also label this as a vector eta dot. This is nothing but the vector of angular velocities, sorry, vector of velocities. It's basically a mixture of linear and angular in inertial frame of reference This will be, you can use this robot Jacobian, cos psi minus sin psi 0, sin psi cos psi 0, 0, 0, 1 multiplied by u v r. And this vector is, we will denote this as zeta, and this matrix is the Jacobian matrix. So eta dot would be j multiplied by zeta. And again, this is nothing but the same vector of velocities. But unlike the previous case, this is expressed in body fixed frame of reference. Body fixed frame of reference. So basically, this relation depicts the kinematics of a mobile robot. The mapping the velocities from the body fixed frame of reference to the inertial frame of references. And as you know, there are two subproblems, what we call as inverse differential kinematics and the second being forward differential kinematics, right? So if the joint vector of the body fixed frame of reference is given, and our problem is to find eta dot, then that problem is forward differential kinematics. And if you are given this eta dot, the velocity is in inertial frame of reference, the problem of finding this vector zeta is inverse differential kinematics, right? Yeah, now moving on, yeah, just like what I've shown here, the kinematic relations are, it could be described by this equation one, and it could also be, represented in a compact matrix and vector form as such. We also know what each of these terms basically represents, right? Yeah, and as I've said earlier, like we also have two subproblems in robot kinematics. One is called the forward kinematics, and the other is called other problem is inverse differential kinematics. So the forward kinematics is analogous to simulating the robot in velocity level, whereas the inverse differential kinematics is analogous to controlling the system at velocity level, right? Then we have also, seen the definitions of some of the degree of maneuverability terms. So what degree of maneuverability is? It's nothing but the sum of its degree of mobility and degree of steerability. And we also know what the degree of mobility is. It's nothing but the degree of freedom the mobile robot manipulates directly through its wheels. And what is degree of steerability? It is nothing but the degree of freedom that a mobile robot directly manipulates by changing the steering configuration. And the sum of degree of mobility and degree of steerability is degree of maneuverability. And this basically determines whether the robot is it'll also give you clues regarding whether the robot is autonomic or not. We'll come to that in later slides. And we also know we could use different kinds of wheels for different configurations. So what you see depicted as green colored wheels, these are passive wheels. These are not driven. And if these wheels are depicted in red color, these wheels are powered using independent motors. And over here, if you see a dot or a ball right at the center of this wheel, that means the wheel is basically a caster wheel. Right? It can rotate about an independent axis, and it can also roll about its axle. Right? And if it is red, then that means both the wheels as well as the caster or the steering is powered. If it is green, then this entire setup is passive. The caster is also not driven. Steering is also passive. The rolling motion is also passive. So then we come to this non-conventional wheel. So the first one over you see is called mechanical wheels. See, apart from like if you consider this to be the primary axle of the wheel, where the wheels will be powered. So on the periphery of these wheels, you will see these passive rollers, these barrel-shaped black-colored rollers. These are not driven; these are actually passive. So that basically enables this wheel to slide along this lateral direction. Like apart from the rolling motion, these rollers will also permit the wheel to slide along this lateral direction. And over to your right is also a similar wheel, what we call as omni wheels. So this will also serve the same purpose. It can roll just like a conventional wheel, and due to this passive rollers, it can also slide, in along the lateral direction. So that was basically pretty much about the topics that we have covered for week one. And we have also seen a question similar to what I have actually presented here. So like it says for a given mobile robot configuration, what is the degree of freedom, what is the degree of mobility, and what is the degree of steerability, right? So we know that degree of freedom is always going to be three because you need three variables to define the configuration of the body. So in this case, this entire rigid body can be represented using this frame of reference that is attached to this body. So you need two coordinates to define its the position, and one another angular coordinate to define its orientation. And the degree of mobility is 2 because there are two driven wheels. And the degree of steerability is also 2 because these two wheels can be steered as required. It can assume any orientation. Yeah, so that was about week one. And on week two, we will continue with our discussions on kinematics. So we extend the kinematics into defining a generalized wheel model. So, like for example, if we have a general case of a mobile robot having a wheel, which can be steered, and it also has you can also assume the generalized robot's wheel as a passive roller that is inclined with respect to this y-axis at an angle phi, right? And the orientation or the difference in orientation between this XCI frame and XBI frame is depicted by this parameter theta I, right? And the direction along which the rollers lie with respect to this YCI axis is depicted as AI, and the radius of the wheel is depicted as AI, the radius of the driven wheels. And dxy and dyi are nothing but the coordinates of x coordinates of this frame of reference Ci with respect to this frame of reference D, right? So the lateral distance is dxi, and the vertical distance along YB is dyi, right? So this corresponds to single wheel, and you can actually develop, you can basically map the angular velocity of each of these wheels, right? Angular velocity omega I of any given wheel to the vector of coordinates, vector of angular velocities with respect to the body fixed frame of reference. So velocity along zeta is nothing but UVR. And using this generalized wheel model, you can get the mapping from zeta to the angular velocity of the wheel. And we have seen different cases, we have seen how to map zeta to the angular velocities of each of these wheels in case of, this is a specific case of differential drive. So if wheel 1 is having an angular velocity of omega 1 and wheel 2 is having an angular velocity of omega 2, you can use this wheel configuration matrix to map omega 1 and omega 2 to UV and R. And you can derive this wheel configuration matrix using the previously mentioned generalized wheel model. So this was the case of a differential drive robot. You can also derive this wheel configuration matrix for a skid steering robot, where all these four wheels are conventional active wheels. And this is the case of a mechanical wheel drive, where you have wheels are actually driven and you also have passive rollers lined at 45 degrees. And this is how your wheel configuration matrix look like. And again, what we also have a different configuration called three-wheeled omni drive. And this is how your wheel configuration matrix would look like, right? So this is basically the conclusion of lectures from week two, right? So this is a typical question that you can expect during your exam. So what it says is that this is about a mechanical wheel robot. You are also given its wheel configuration matrix as so. We have already seen this is a mechanical wheel robot. In the question, you are also given this wheel configuration matrix. And the question also asks or demands your robot is supposed to move diagonally in the first quadrants, by keeping the same initial orientation. Then what will be the correct combination of this wheel angular velocities, right? So you know this relation zeta is W multiplied by omega. This omega is nothing but the vector of wheel angular velocities, right? And W is given in the question. And as per the question, your robot should move diagonally along the first quadrant. So from the question, you can also assemble how your zeta vector would look like, right? It should look something like k, and 0, where this is the u component, this is the v component, and this is the r component, right? So if u and v are constant, the robot will keep its original orientation and it will move diagonally, right? It will have equal angular velocities along xb and yb, right? And since r is 0, this robot will keep using its original configuration. It won't have any angular component. It won't rotate. So since W is known, right? Since W is known from the question, it is given in the question. And since we can also deduce zeta based on the question's requirement, as it should move diagonally, then our objective is to find omega, the right combination of omega 1, omega 2, omega 3, omega 4. So if you solve this, you will find that option 3 is the correct answer, right? Omega 1 is omega, omega 2 is 0, omega 3 is omega, omega 4 is 0. So if you plug option 3 onto this equation, W multiplied by omega, you will get zeta as this form, K and 0, where K is any constant, right? So you can expect similar questions. So instead of the robot moving diagonally, you may be asked what will be the correct angular velocity combinations when the robot moves laterally instead of diagonally, right? So that is a typical question you can expect for your exams. And moving to week 3, so we now move away from kinematics. Now we start our studies on dynamics of wheel mobile robots. So these are the topics that we have covered for dynamics. Actually, we defined what dynamics is. We have also seen, the derivations of equations of motion of a mobile robot. So we have done this using two different approaches. The one is called Euler-Lagrange method, which is based on total energy of the robot. And the second be, based on principle of conservation of momentum, that is Newton-Euler method. So we have basically derived this equation of robot. If you can recall the lecture videos, we have derived these equations of motion through both of these methods, Euler-Lagrange method as well as Newton-Euler method. And we have also seen how the different wheel configuration of a robot, affects the dynamics of a wheel mobile robot. Influence of wheel configuration on dynamics. Similar to what we have seen in kinematics, where we have defined the wheel configuration matrix. Yeah, so we basically covered, or we have reviewed what dynamics means. So in robot, dynamics basically means a study of change of state of a system. And in robotics, it basically, involves, involves motion actually. Change of state basically involves motion, right? So when we study dynamics, we also cover why and how the motion occurs when forces and moments are applied on the bodies. What actually causes the motion, right? And we also derive this equation of motion, which is essentially design, analysis, and control of the system. So equations of motion will give you the, like, if the effect of forces, inertia, all these things onto the general, strength or reaction forces acting on each of these joints, which will enable you to design the linkages. And you can also do this analysis based on the dynamics, and it will also help you to design an appropriate motion controller for your problem. And essentially, you can basically represent dynamics of a mobile robot using this, expression, which maps this vector torque, torque acting at each of the generalized coordinates, mapping it to, the trajectory of the mobile robot, like eta dot and eta double dot. So if you have a trajectory, if you supply a trajectory to a mobile robot, having its own mass and inertia, what will be the corresponding actuator torques that we need to supply in order for us to realize this this trajectory. And yeah, just like what we have seen in the case of kinematics, dynamics also has two subproblems. One is called forward dynamics, the second being inverse dynamics. And the key difference is that, like, if you supply the actuation torque or the input actuation torque, what will be the resulting motion look like? The position, velocities, and accelerations. So this is nothing but forward dynamics problem. And in case of an inverse dynamics problem, if we want the robot to realize or to track this a desired trajectory, defined by eta dot and eta double dot, then finding out the required input torque to achieve this trajectory is a problem of inverse dynamics. Right? Now what we have seen, we have also used both of these methods, to derive these equations of motion, which can be represented using this, matrix vector compact form, such where this vector over here, fx, fy, and mz, is the vector tau, and what you see over here is this mass matrix D, which is also symmetric matrix, and this vector u dot, v dot, and r dot is the vector of accelerations, that is zeta dot, and over here is a vector comprising of this fx due to Coriolis and centrifugal effects, that is this term n of zeta. And you can derive these equations of motion using either of this Euler-Lagrange method or Newton-Euler method. And fx, fy, and mz are the forces along this xb axis, fy is the force along yb axis, and mz is the moment about zb axis, where this xb, yb, and zb are axes fixed to the body. And all these parameters, m is nothing but the mass of the mobile robot. ICZ basically is nothing but the moment of inertia of the robot about the vertical z-axis. XBC, YBC is the offset, the offset of the center of mass with respect to the body fixed frame of reference. Because you cannot always expect the center of mass to lie or center of gravity to lie exactly on the body fixed frame of reference. So that is about it. Then, yeah, we have also seen how to represent the equations of motion in inertial frame of reference. Right? Earlier in this case, see, all these terms are represented with respect to body fixed frame of reference. Right? Fx, my, and mz, these are all with respect to body fixed frame of reference. And D are all defined with respect to the center, the body fixed frame of reference, because XBC and YBC are defined with respect to the body fixed frame of reference. Zeta inherently is defined with respect to body fixed frame of reference, and so is n of zeta. And if you want to transpose everything to inertial frame of reference, you can do so by using the principle of conservation of power, which is nothing but power on the power of the robot in inertial frame is equal to the power to move the robot at body fixed frame of reference. You can express this conservation of power mathematically using this expression, where tau of eta is the wrench or the force and moment vector in inertial frame of reference. Eta dot is the velocity of the mobile robot with respect to the inertial frame of reference, and tau and zeta are the forces and the velocities in body fixed frame of reference. And you also know from kinematics, you can map the velocity from body fixed frame of reference to the velocities to the inertial frame of reference. And from these two equations, you will be able to derive, or from these two equations combined with this dynamics equations of motion, you will be able to finally derive the equations of motion in inertial frame of reference, where tau n is the torque with respect to the forces and moments represented with respect to the fixed frame of reference. D of eta is the mass matrix with respect to the inertial frame of reference. Eta double dot is the vector of accelerations, again with respect to the inertial frame of reference. And the same in the case of this vector n. And the full expansion of this vector d of eta is given using this expression. D of eta is nothing but j d j transpose, where d of zeta is the mass matrix with respect to body fixed frame of reference. And n of eta is given as such, minus j d j inverse j dot zeta plus j of n zeta. Right? So that is how you can define equations of motion in inertial frame of reference. And similar to how we have seen in the case of kinematics, we can further extend this mapping, from fxmi and mz to the traction forces available at the wheels, where fx is the force along xb axis, fy is the force along yb axis, and fz is the torque along zb axis. And f1 and f2 are the traction forces available at both of these wheels. So if you consider this equilibrium of this entire robot chassis, if you resolve all the forces and moments with respect to fx, fy, and mz, you will end up with these three equations, and you can represent them using this vector matrix relations. So fx, fy, and mz are related to f1 and f2 using this dynamic wheel configuration matrix. So this is the case of a differential wheel while robot. The same can be done in the case of an omni-wheel robot, where this is the dynamic wheel configuration matrix, and F1, F2, F3 are the traction forces at wheels 1, 2, and 3 respectively. And this is in the case of a tricycle, where you can map Fx, Fy, Mz to F1, because we only have a singular or only a single driving wheel that is also steerable. So here, instead of a vector, we only have a scalar f. And this is the wheel configuration matrix in dynamics. And similar thing for mechanical wheel drive, you can use this dynamic wheel configuration matrix to map fx, fy, and mz to all the four traction forces, f1, f2, f3, and f4. Okay, so this is a typical question that you can expect from this topic. If you are given an inertial matrix, B, inertia matrix of a mobile robot with respect to body fixed frame of reference, B of zeta is given. And you're also given that the robot is oriented 60 degrees with respect to the inertial frame of reference. So you can also assemble this Jacobian matrix as cos 60 minus sine 60, 0, sine 60, cos 60, 0, 0, 0, and 1. And you are asked to find the inertial matrix with respect to this inertial frame of reference. And as you have already seen, the mapping between both of these coordinates is d of eta is j d j transpose. So d of eta is j d of zeta j transpose. So if you plug this Jacobian here, here, and if you plug this D matrix here, and if you solve this matrix multiplication, you will get this matrix D of eta as option 2, right? Yeah, so that was about lectures on week 3. And for week 4, we start topics regarding from week 4 onwards, week 4, week 5, and week 6, we cover topics on perception. This is on week 4, and on week 5, we cover topics on localization. And on week 6, we cover topics on path planning or navigation, right? So we'll first cover all the topics, relevant topics that we have studied in week 4. So week 4 was more about sensing and perception. The different kinds of sensors that we are using. How can we classify the different sensors based on their operations and so forth, right? And we also began this section, this series of lecture weeks 4, 5, and 6 by analyzing this general control scheme of a mobile robot. We start by gathering information from the real world environment using sensors, and whatever raw data that we are getting from the sensors, we'll extract it, and using a preloaded map or a map that has been given out to the robot will localize itself on that uh, uh, offline map. It will localize in the sense it will identify its current position on this map, and then further it will basically create a planning, to traverse or to travel from its current position to its goal position. And once it has actually created a planned path, it will actually send this path planning to a motion controller, which will send the right commands to the actuator so that the robot can start moving and reach its final goal position. And this cycle goes continuously on and on. And we also covers what perception means. It is nothing but the process by which people translates sensory information into coherent, unified view of the world around them. So this is also pretty much relevant to mobile robots. So from the sensors, it sees pretty much everything. And by perception, it only extracts what it is required to see from all the raw data it is actually getting from the sensors. And we have also seen the different sub steps or the sub systems of a perception problem. The first is obtaining data from the sensors, then we'll extract the features, necessary features, then we'll match the features with our requirements, and it then updates. Then once it has actually recognized, it will give new commands to the model. The model will do appropriate calculations, and then finally it will be given to the model using some motion controller. Then it will finally predict its current location. For that, it can localize itself. Right? Then we have also seen, now we get on to the topics of sensors. How do we classify sensors? So there are basically two ways we can classify sensors, which is called proprioceptive sensors and exteroceptive sensors. So proprioceptive sensors are basically those which measures value internally to a robotic system. And exteroceptive sensors are those which, gathers information from the robot's environment. So this is one way of classifying robot sensors, proprioceptive or exteroceptive. The second way of classifying robot sensors is whether the sensor is active or whether the sensor is passive. So in the case of passive sensors, they utilize energy from environment. It does not need, we do not need to supply energy to the passive sensors. Whereas in the case of active sensors, they emit energy and measure their reaction. And inherently they offer better performances, but because since they are emitting energy, they will leave some sort of a footprint on the environment. And actually, we have seen different kinds of sensors, For example, if you take a look at tactile sensors, there are different kinds of tactile sensors over here. And you can classify all of these to be either exteroceptive or active. So this column corresponds to whether the sensor is exteroceptive or proprioceptive, and this column, this column basically denotes whether the sensor is active or passive. So we basically tabulated a wide variety of sensors, be it tactile sensors, wheel motor sensors, heading sensors, ground-based location sensors, ranging sensors, speed sensors, vision-based sensors, whether they are passive sensor or active sensors, whether they are proprioceptive or exteroceptive. So we have basically made a comprehensive compilation of all the relevant sensors that we would be using in mobile robots. And yeah, this is a typical question that you can expect for week 4. You have to, match the following from the left-hand column to the right-hand column, right? So basically, a general classification of sensors is given here, and you have to appropriately match it with the right example. For example, this tactile sensors, this contact switches is an example of a tactile sensor. That is also a passive sensor. And what about wheel motor sensors? If we have encoders is an example of a wheel motor sensor. And similarly, CCD cameras is an example of vision-based sensors. Right? So once you do this match the following, the correct answer would be option D. Right? Option D would be the right way of matching the general classification of sensors to an appropriate example. Okay, and so now we move on to week 5, basically. So now that we have covered basic topics on basic topics on perception, we now cover topics on localization. So basically, localization, we could do two different kinds of approaches. One is called Markov localization, the other be Kalman filter localization. We have also seen either of these cases in detail in the weekly lectures. We have also discussed either of them during our live sessions, right? And we have also roughly seen what are the different steps in localization. So it basically consists of uh, two different steps. So the one is called prediction, and the second would be perception. Right? So if you begin with uh, if you begin with here, actually, whatever the sensor is observed and whatever the robot is actually predicting, it should be matching, right? The robot will be predicting its current position to be something using its odometry, using its own encoder data. That is one channel of information. And the remaining channel would be from its sensors, what the robot is actually seeing. The robot says it should be in this position, and the sensor is saying it should be in this position, right? And if both of this is matching, then only the robot can actually confidently say that the robot is in the exact position. Otherwise, if it is not matching, then the robot will have to do some appropriate adjustments or estimations, and later it will further adjust. Later it will further adjust its new prediction. Right? So this is basically an ongoing process. It keeps going on and on. One channel of information is from this encoder internal to the robot, and another channel of information is from the sensors. Right. And what are the challenges that we have seen for localization? So the first being, knowing the absolute position using GPS is not sufficient because GPS is not suitable for indoors, and their accuracy is, if you need accuracies to the millimeter level, GPS would not be sufficient. and localization in human scale in relation with the environment. GPS will not be able to provide human scale localization. And planning in cognition step requires more than only position as input. You cannot just plan a path with just a position. You need also information from all the sensors. And you also have these challenges, sensor noise, is due to the fact that other environmental factors could influence the readings that we obtain from the sensors. We also have sensor aliasing. If the sensor, for example, if the sensor is not sampling, if the sensor is not sampling uh, with the current correct frequency, the signal that we are measuring is one frequency and the sampling rate is completely different, then we may not even get the correct signal. So that is what sensor aliasing is. Effector noise. If there are noise from the motors, from the actuators, and there are also errors from odometric position. Because as you will see in the later slides, everything will be based on uncertainties, and as a result, we cannot fully rely on odometry. Right. So if, for example, if the wheels slip or if the wheels are actually not rolling as per the model, we may end up with a large error because the error gets accumulated. And once it goes beyond a limit, then we cannot really, the whatever information that we get from the odometry will be, rendered useless. So that is why we need perception. In order for that, it can easily complement with data from odometry. And if you talk about odometry, there are different kinds of errors. One classification, one is what we call deterministic errors. As its name says, it is deterministic. We can identify the source of these errors and we can also eliminate these errors. And the second being non-deterministic errors, because we cannot really eliminate these non-deterministic errors. They are also called as, random errors. Right? And we have also seen, the major source of these errors, it could be due to this limited resolution during integration, because from the accelerometer, we'll be only getting accelerations. If you want to get velocities and positions, you will have to integrate this discrete data. And if your step size is actually very low, your accuracy during while doing this numerical integration would not be ideal. And there could be factors due to fabrication, such as misalignment of wheels and probably unequal wheel diameters. All these factors are deterministic. You can eliminate them. And there are other cases, variation of contact points of wheel. You cannot exactly model or you cannot exactly make the wheel exactly to behave how you want to do. Unequal floor contacts, these are all, undeterministic or non-deterministic random errors, right? So these are the various kinds of errors that you would encounter or that you will be, suffering during odometry. And yeah, basically the odometry you can, for a small incremental change of displacement of wheels, you can basically get to know what will be the incremental change of position of this frame of reference. That is what we use in this expressions. Where delta x is the marginal change of position in along x-axis, delta y is the marginal change of position along y-axis, delta theta is nothing but the marginal change in its angular position, and delta s and delta r are the marginal displacement along marginal displacement of right and left wheels. And b is nothing but the width of the chassis. Right? So you can actually use maybe a Taylor series approximation, like for an for an incremental change. If the robot starts from an initial position, then what will be the new position for an incremental change? That is actually given by this expression, right? And later, we also have seen how this error propagates. because the error propagation is also described with a lot of assumptions, because we assume that the model uh, we assume that the error assumes a uh, normal distribution like this bell curve, right? And as a result, if you know the uncertainty in inputs, uncertainty in sensor inputs, what will be the uncertainty in outputs? Like for example, if you know the uncertainty of an input, defined by this coordinate x, these are the uncertainties. Then if you also know the mapping, y as f of x, what will be the uncertainty in the output y? So that is, you can obtain that by using this mapping, fx cx fx transpose, where cx is the input covariance matrix, and cy is the output covariance matrix, and fx is nothing but the Jacobian, that is basically a mapping between the coordinates of input and coordinates of output, right? So yeah, if you want to know the uncertainty in position, you can use the same expression fx cx fx transpose. So this is the uncertainty in position, uncertainty in position obtained from odometry, and this is the uncertainty from the sensors. So the uncertainty in the position is actually the sum of uncertainty from odometry and uncertainty from sensors. And all of these terms, this zeta p, uncertainty in position, you can actually obtain it. It's basically the Jacobian matrix. You can obtain it by taking the derivative of this expression. And z this sigma delta is the uncertainty or the covariance matrix of sensors, which will be mostly a diagonal matrix as such. And delta SR and delta SL, as you know, the uncertainty is actually directly proportional to the infinitesimal change of wheel motion. And where this FP and this F delta RL, these Jacobian matrices are all defined by these parameters, these matrices. And as you know, if you see as the robot actually propagates, you can see that as time increases, this sigma p matrix, this sigma p dash matrix will be getting larger and larger as time progresses. Unless you get some sensor data and you compensate or you correct it, this sigma p will keep on growing, right? As depicted by this. So initially, from the initial condition, initially we are fully aware of the position of the robot, so the uncertainty is quite minimal. And as you see, as the robot propagates or as the robot moves through time, the uncertainty, the region of uncertainty basically increases like such. And another thing to note is that the uncertainty is actually the highest in a direction perpendicular to the direction of motion of the robot. For example, if the robot is moving tangential, if the robot is moving like this along this path, at this position, the direction of motion would be tangent to this curve. And you see that the uncertainty is least along the direction of motion, and the uncertainty is highest to along a direction that is perpendicular to the direction of motion. Right? Then we have also seen, probabilistic map-based localization. We have, in general, we have actually seen problem because we are uncertain about where our location is. So we can use probability theory to have an estimate on, where the robot could be, what is the probability that the robot could be in any of these locations, right? And we have also seen these terms such as belief state, or the perception update. It basically denotes the belief state is basically, or the perception state basically denotes the probability that the robot is at location xt, right? Given all the sensor readings until time t and all the control inputs until time perception after the sensor reading has been taken care of. And this bell bar xt, it's also called prediction state. So this is basically the probability that the robot is at position xt before taking any measurements from the sensor. Before getting the measurement from the sensor and from all the control inputs. If you know the information of all the control inputs. So prediction, before the sensor data, and perception after the data from the sensors. And yeah, again, we also have seen various cases of localization. We use this Markov localization, using this prediction update, bell bar xt, before the sensor data is obtained, and the perception update, the correct where once you obtain the prediction update, sorry, once you update the sensor data, bell of xt or the perception update would be p of zt such that xt and m is given multiplied by the prediction update bell bar of xt. Right? We have also seen an example on how to implement this Markov localization. So basically, for first process is basically discretizing this entire grid into multiple fine grids or multiple subpositions, and that inherently makes it much a bit computationally inefficient compared to this other case called Kalman filter localization. So compared with Markov, this is inherently more efficient and precise. It does not really have to discretize this entire grid. But the problem is that if the uncertainty grows or it becomes too large, that Kalman filter basically will fail. It cannot, uh, it cannot regroup or it cannot recover from a large uncertainty. Whereas in the case of Markov localization, it can recover from a very huge case of uncertainties. And there is also another term called slab, where in the earlier cases, the map of the environment will be given onto the robot. But in case of SLAM, it also simultaneously builds the map while it is also localization. SLAM is a process by which a mobile robot can build a map of an environment and at the same time use this map to deduce its location. So it will build a map and it will also locate itself on this map simultaneously. Right? That is about SLAM. And yeah, this is a typical question you can expect from week 5 worth content of lectures. You have to choose the true statement out of all these 4 options. The first being prediction update is based on updated belief state. Is it true or false? That is actually false because prediction is actually based on the previous belief state actually. Perception update decreases the uncertainty of the robot. That is true. Because prediction update, keeps on increasing the uncertainty and perception, when you combine or when you club the prediction update with the information from the sensors, the uncertainty will get reduced. So perception update definitely decreases the uncertainty of the robot. Action update is based on prior belief state. That is also true. So basically, action update is another name for prediction update. Both are basically the same. Right? It's based on prior belief state, prior control inputs, And what about D? Prediction update increases the uncertainty as the robot. That is also true because it relies purely on odometric data. And if there is some issues with the sensing or if the wheels are slipping, whatever information that we get from the prediction update, that could be false or that could be highly inaccurate. So prediction update alone will definitely increase the uncertainty of the robot, and it can only be brought back or the accuracy can only be increased when you fuse it with the information that you obtain it from the sensors. Yeah, so that was about week 5 worth of lectures. And what about week 6? So in week 6, we, consider the topics on navigation. We also talk about path planning. We also talk about different graph search methods, and introduce we also got introduced to path planning and a couple of obstacle avoidance algorithms. So navigation basically comprises of creating a roadmap. If you have an environment, you need to create a comprehensive roadmap. All the possible combination of paths from a start position to an end position. It could be you could go in multiple ways without tackling any of these obstacles. And once you have created a roadmap, that creation of a roadmap is called graph construction. And once you have created a graph or a roadmap, what will be the optimal path to take from the start position to the goal position? So that is what we deal on graph search methods, graph construction and graph search. So these are basically the subproblems of a path planning. So yeah, we'll now deal with navigation. So we have covered perception and localization. Now we are around in this part, navigation. And once we have created the path, or once we have fully defined the path, then the information will be sent on to the motion controller, which will give the commands to the actuators. So what does navigation say? Navigation is given a partial knowledge about its environment and a goal position or sensor of a series of positions. Navigation encompasses the ability of the robot to act based on its knowledge and sensor values so as to reach its goal position as efficiently and reliably as possible. So, like as you say, there are multiple ways that you could reach from a start position to a goal position, and navigation basically deals with finding the most optimal path so that you can reach it more efficiently and reliably as well. Yeah, and these were the important sub-problems of navigation. One is path planning, identifying the trajectory that will cause the robot to reach its goal position, and the other is obstacle avoidance. So as you know, the environment will be dealt with multiple objectives, and how will the robot tackle these objectives, obstacles? Will it cannot obviously go through. It have to have some sort of algorithm so that it can navigate through these obstacles and to reach its final position. So that is what obstacle avoidance is about. And while doing this navigation, or while modeling or modeling navigations, there are a few important assumptions. We consider the robot to be holonomic. For instance, the robot can move forward and backward. It can move side to side in lateral direction. It can move diagonally by keeping its orientation fixed. It can also rotate about its own axis. So the robot is holonomic. It's not limited by any sort of movements. And we also assume that the robot is a point. Instead of having a physical dimension, we assume the robot to be of a point. Right? But we have to do appropriate compensation because we have reduced the size of the robot to a point. The obstacles must be inflated by the size of the robot's radius to compensate for it. For example, in the case, if you consider this to be an obstacle and this to be a robot, so as the boundary of the robot touches this obstacle, it'll basically collide. That is how we define collision. But in navigation, what we do is that we consider the robot to be a point, right? And in order for us to compensate for this, in order for to compensate this shrinkage of dimension, we will inflate this obstacle by an amount equivalent to the radius of the robot. Obstacle is inflated so that both of these cases will be equivalent. So that is also another assumption that we do for navigation. Yeah, and now we go on path planning. And as I've already said, path planning has two different approaches. two different sub-problems. The one is called graph search and the other one is called graph construction, right? And graph construction is the first point where we would construct these roadmaps. There are different methods of graph construction, which are called visibility graph, Voronoi diagram, and cell decomposition methods. And once the roadmap was created, we could have multiple possibilities to go from start position to the goal position. And once the roadmap has been completed, we'll go on to graph search problem, which is to find the optimal path to reach, to start from the start position to reach a goal position. So we'll move on to these different kinds of graph construction problems. The first being visibility graph. So we have a start position, we have a goal position, and these what we call these polynomials, what you see here are the obstacles actually. The visibility graph for a polynomial configuration space consists of edges joining all pairs of vertices that can see each other. So what does that mean? So this vertex can see this vertex, it can see this vertex can see this vertex. So all possible vertices that is within the line of sight of the corresponding vertex is marked or is connected. And similarly for this vertex, you can see this vertex can see this vertex, also see this vertex. So once all these vertices are connected, the line of sights are connected. The peculiarity of this visibility graph is that the robot will actually move as close as possible to this obstacle so that it will reach the goal. And most often, the path that is as close as possible to the obstacles will be the optimal path. It does not really shy away, or hesitate to, reach or to get near, get near to the obstacles, as close as possible, right? So yeah, that is about visibility graph. If the robot does not have any hesitation to reach to get as close as possible to these obstacles. And the second method is actually called Voronoi diagram. So this is exactly opposite to what we have seen here. The robot will actually take a path that is as far as possible from the obstacles. Right? So if this is an obstacle, a boundary wall, and if this is the boundary of another obstacle, the robot will actually try to maximize the distance between either of these two obstacles. So it will stay away from these obstacles as far as possible, and it will also try to create a roadmap as such. And the potential drawback of this method is that if the obstacles are actually too far away, then maybe if it is beyond a threshold, the robot may not be able to find the boundaries with its sensors, right? If the robot is using short range sensors, it may not be able to detect the boundaries anymore after a point of time. So it's probable that the robot can get lost. That is about Voronoi diagram. So and the third is cell decomposition method. So it deals with discretizing the environment into multiple cells, right? So the boundary of the cells is based on geometric criticality. So these are the critical points, actually, the vertices. And the resulting cells are either completely free or completely occupied. Whether the cell is completely free or whether it is completely free or whether it is completely occupied. And yeah, the basic abstraction behind such decomposition is that the particular position of the robot within each cell of the robot does not matter. So in this case, whether the robot is here, if the robot is in cell 1, that alone is enough. The particular position within a cell is not really of a matter of concern. The robot can be here or here or here. So as long as the robot is anywhere within the cell, that is fine. So in that case, you can actually use, these sort of algorithms, right? And the key disadvantage of exact cell decomposition is that the number of cells and therefore the overall computational planning efficiency depends on the efficiency and complexity of objects in the environment, right? So if there are only a few objects or a few obstacles in the environment, the number of cells would be very few, right? If the number of cells is very few, you will also, the resolution of the robot's position will also suffer accordingly. So in that case, since it is purely dependent on the number of cells, which is influenced by the number of obstacles, it may not be very reliable in case of a dynamic environment. And the remaining would be approximate cell decomposition, where you would discretize this entire grid using multiple grids or the entire environment into multiple grids. And based on whether the obstacle occupies a cell or not, you can actually classify whether an obstacle, occupies it or not. So as you see, now the representation is actually more or less pixelated. And as a result, if you have a narrow passageway like this, there is a chance that, once you do this approximate tessellation, once you do this, there is a chance that you may lose all these narrow passageways. So it's possible for narrow passageways to be lost during such transformation because of this, discretization. So ideally, the optimal path would have been like this. But since this path is blocked, since this path is no longer available, the robot will have to take another path. Now, we have covered all the graph construction method. Next would be graph search method, to identify the optimal path, out of all these different paths, which of path is actually taken. So that is more or less, solved by, finding or minimizing this objective function, to decide on which path to select first. And the objective function could be anything. So mostly we would minimize this cost function, which is nothing but the sum of expected cost and this term called heuristic cost. Expected cost is nothing but cost of traveling from one node to another node. And heuristic cost is basically the distance between the current position and the goal position. And depending on how this expected cost and this heuristic cost varies, we can have multiple graph search algorithms. And there are also multiple, philosophies to, explore all the nodes. The one is called breadth first. It begins from a start node and explores all the neighboring nodes, right? So, for example, if you have nodes like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what it does is it first explores all its neighboring nodes. So if it begins from 1, it will explore 2, 3, and 4. Then from 2, the neighboring nodes are 5 and 6. It will explore 5 and 6. Then the next level would be 3. And the neighboring nodes of 3 would be 7 and 8. Then it will actually explore 4. And its neighboring nodes is 4, 9, and 10. It explores all the neighboring nodes. And that is how it propagates. Whereas in case of a depth first, it expands each node to its deepest level. For example, if it starts from 1, it will expand from 1 to 2 to 5. Like this, it will go to its deepest level. Then it will backtrack, right? It will backtrack, then it will expand again to its deepest level. And if there are no further nodes to be explored, it will again backtrack. Since all the nodes from here is explored, it will again backtrack to this node. It will go like this, right? That is how this depth first approach works. Each node expands each node to its deepest level of the graph until the node has no more successors, right? the search may backtrack. So once there is nothing else to be explored, then the depth first will backtrack and again do this depth first exploration. Yeah, and one example of this breadth first algorithm is this grass-fire algorithm, where it starts from a start position and cost of moving to the next node is 1 unit and cost of moving to this node would be two units. And just like how a grass-fire spreads, this the cost function will spread from this origin all the way to this goal position. And you can actually find the optimal path, which will give you the least cost. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9. This is an optimal path. And you could also have multiple optimal paths 1, 2, 3, 4, 5, 6, 7. Sorry, you can have, this is an optimal path. And this 1, 2, 3, 4, 5, 6, 7. This is another optimal path. This is optimal path. And this is also an optimal path. So you can have multiple optimal paths actually based on how this grass-fire algorithm propagates. And again, there is also another thing, what we call as this Dijkstra algorithm. So earlier was grass-fire algorithm where cost of travel from one node to another is equal actually. It's only 1 unit, from this position to this position, cost of travel is only 1 unit. And from here to here, it is only 1 unit. Whereas in case of Dijkstra algorithm, the cost of traveling from one node to another is actually varying. Right? From node S to node 2, it is 9 units. From 2 to 3, it's 24 units. Right? So this is also similar to a breadth first algorithm. So you first, assign the cost of all the nodes to be infinity, right? Then you expand this node along the node that is least cost. So if you expand along this, you can replace this infinity by 9 because this will be basically taking the least amount of cost. And if you carry on this, if you further expand the node which has the least cost, you will finally end up with you will again actually finally end up with the goal position. And if you backtrack from this goal position all the way back to the start position along the path which will give you the least cost, then that would be the most optimal path. Right? So subsequently, the cheapest state on the heap is extracted and expanded. This continues until the goal node is expanded. The solution can then be backtracked from goal to the start. So whichever path gives you the least cost, it can be backtracked from the goal position to the start position. And there is also another thing called an A-star algorithm, where, as you can recall, the path cost is expected total cost is the path cost and heuristic cost. And in the earlier case of grass-fire algorithm and Dijkstra algorithm, we consider heuristic cost to be 0. Whereas in the case of A-star algorithm, the heuristic cost is actually not 0. And heuristic cost is defined as the distance of any cell from the goal in the absence of obstacle cells. Right? So this is also similar to this grass-fire algorithm, but here you will also have this heuristic cost. And whichever gives you the minimum sum of, whichever path that will give you the minimum sum of expected cost and heuristic cost, that will be your optimal path. So in this instance, the optimal path to reach from start position to the goal position would be this path. And there is also another kind of another way of path planning. It's called potential field path planning, where you treat the robot as a point that is moving under a potential field, right? It will move as per the influence of this potential field, and basically the goal position act as an attractive force, and the obstacles at the start positions attracts as the repulsive force. At any given point, the superposition of all the points on the robot will determine its, its propagation or its direction of travel. Yeah, and we conclude week two by algorithms on obstacle avoidance, where we have seen two different algorithms called bug one and bug two algorithms. Where in bug one algorithm, the robot fully encircles the obstacles and departs from a point which is which has the least distance to the next obstacle. And bug two, it does not fully encircle the obstacle; it will leave from the earliest possible opportunity. And this was actually a typical question that you can expect. Which of the graph construction method matches with the following sentence? Robot path comes as close as possible to the obstacles, resulting the optimal paths are minimum length solutions. So visibility graph is the correct answer, because it gets as close as possible to the obstacles. Voronoi diagram is not the correct answer. Cell decomposition is also not the correct answer. So indeed the correct answer is visibility graph. If you are still in doubt, you can, revisit the previous slides. And on week 7, we will discuss, the development of motion controllers. We gave a brief introduction to motion controllers. We have seen, dynamic kinematic control, without considering the dynamic effects. We have also seen, dynamic controllers, and for either of these cases, we have seen open loop and closed loop implementations. Yeah, and we basically, started the session with motion control. Why is it relevant? Why do we need motion controllers? Because most of the time we cannot exactly obtain the dynamic model of a system, because of external disturbances and parameter variations, maybe due to joint clearances, we cannot exactly model the dynamics of the robot. And as a result, we need motion controller, to compensate for those, unmodeled effects. And during the introductory lectures, we have also seen, different trends that we have employed in robotics, from mid 1970s all the way to the current era or the current decade, starting from 2015. We started with exact models, without any sensors, and now we basically have reached data-driven models. We have also, seen how to seamlessly fuse inaccurate models and limited sensing capabilities, so that we can realistically simulate or realistically capture the dynamics of wild robots. Yeah, and there we have also seen various classification of robots, whether it is model-free robot, purely based on sensing, and model-based control methods, where it is free from any sensing, it is purely relied on the dynamic model. That is also an open loop implementation. And we began with kinematic control of mobile robot. And within kinematic control, we have seen open loop and closed loop implementations. So we have seen what are the desired parameters. In case of kinematic control, we want the robot to track a desired trajectory defined by eta d and eta dot d. We have all these parameters available, and our objective is to find out zeta, the controlling. And our objective is, as time tends to infinity, the actual trajectory should bend to the desired trajectory, right? So in case of an open loop control, zeta dot is nothing but J inverse eta desired dot. This is nothing but an open loop control. And there are a few limitations for this open loop control, which are like if the initial position of the desired trajectory, initial velocity of the desired trajectory is not equal to the initial position of the actual trajectory, then this will not work. And if eta desired dot is 0, then control input will be 0, and again this will not work. And we have seen the closed loop implementation of kinematic control, which is defined by this law. Zeta is J inverse eta multiplied by eta desired dot. So this is the desired velocities. This is the feed forward term, and multiplied by a lambda eta tilde dot. This is the difference between desired and actual position. So this is basically the feedback term that makes it closed loop. So this is the kinematic control in closed loop actually. This is also called as a computed velocity controller. And similarly, in the case, we have also seen various cases of dynamic control. We have also seen open loop and closed loop implementations of dynamic control. And similarly, our requirements are, to track a desired trajectory, eta, desired dot, and desired double dot. And these are the available parameters. So apart from kinematics, these are all available since kinematics. And apart from that, since we are considering dynamics, the inertia metrics and the vector of Coriolis and centrifugal effects are also known. And our objective is to find out the control input vector tau, right? To find out tau such that as time tend to infinity, the errors will tend to zero. And as per this inverse dynamics, this was the feed forward implementation or the open loop implementation, right? If you know the desired trajectory, you can easily know the desired control input, right? Where you can substitute the zeta desired dot using this expression. So if you know this zeta desired dot, or if you know this zeta desired dot, your objective is to find tau, and this is how you obtain this. So this is again a purely feed forward control or an open loop control without any feedback terms. And if you want to do this feedback, if you want to eliminate these errors, which is more robust compared to a feed forward law, you want the system to behave as per this differential equation. You want the error dynamics to follow this differential equation, eta tilde double dot plus k1 eta tilde dot plus k2 e2 tilde dot. So if you force the system to behave as per this differential equation, so as time tend to infinity, eta dot, eta tilde, they all both tend to zero. If you force the system to behave as per this differential equation. And if you select this control input, defined by tau, if this is your control input to the system, your error dynamics will behave as such, right? If this is the control input to the system that you would supply to the actuators, the system will behave as per this error dynamics law. And here, this is the feed forward term, open loop term, and this eta tilde dot and eta tilde, these are the feedback terms. Feedback, because this is the difference between actual velocity and desired velocity. This is the difference between actual position and desired position. Actual position is what you get from the sensors as a feedback. And this is a typical question regarding week 6 lectures. So the controller of land-based holonomic mobile robot is required to have the following aerodynamics. This is a first order aerodynamics. So how will you select the kinematic, the kinematic control law? So if you select this control law, this kinematic control law, you would be able to obtain this aerodynamics. You can cross-verify this using the lectures. So typically this will be, you can expect similar questions. So this is only in the kinematic level. So in case if you are asked to find out, if you want the system to follow this aerodynamics, now this becomes a dynamic problem. This is a second order ordinary differential equation. And in that case, you will be also asked to find out the control input tau. Right? This could be a possible question for your final exam. And for the last week 8 lectures, we cover all the different kinds of, we explore other systems of mobile robots, whether it is legged, whether it is, aerial, whether it is, underwater robots. And we also cover something called multi-robot systems, where multiple robots collaborate to achieve a common goal. And the purpose of this multi-robot system is to, we have seen the multiple, the common motivations for developing a multi-robot system. If the task is actually too complex for a single robot to, pursue, or for a single robot to accomplish, right? And if the if the task is much efficient if you use multiple robots using parallelism, and having multiple robots will also increase its robustness. So these are the common motivations for pursuing multi-robot systems. And you can also classify this multi-robot system based on the kind of robots that are collaborating within the system, right? So in case of a collective swarm system, this will be comprised of homogeneous robots. So each and every robot will be identical, and all the robots within collective swarm would have minimal knowledge about the other members. Whereas in case of intensely cooperative systems, it could be they may have some sort of awareness about what other team members are doing, because they have to do a coherent collaborative action. In case of weakly cooperative systems, it can also accommodate homogeneous, like heterogeneous robotic systems. Each and every team members could be of different configuration, heterogeneous. And we have also seen different kinds of control architectures, of a multi-robot system, whether it is centralized, where we have a central server which will monitor all the uh, sub servers, or the constituent members of a robotic system. And we have hierarchical system where the tasks will be delegated to the subsequent levels. It's similarly to the military order of command. And we have decentralized, where each and every robot will be given its own task, and they can operate independently. They don't need to know what others are doing. And we also have this hybrid, which is basically a combination of hierarchical and decentralized. We have seen these sort of things. And we have also seen the difference between autonomous mobile robot and automated guided vehicles. Where in the case of autonomous mobile robot, the AMRs, they are capable of navigating in an uncontrolled environment without the need of a physical or electrochemical mechanical guidance device. Whereas in case of AGVs, they only work on constrained workspaces, maybe in warehouses and all those things, and their routes are actually predefined. Their routes are actually strictly controlled. And we have also seen the differences between AGVs and AMRs, where they would be employed, you know, uh, their applications and all those things. And we in the subsequent lectures, we have seen different solutions of mobile manipulators. This is a mobile manipulator actually, where a manipulator R is attached on top of a vehicle. And this is also another mobile manipulator, where in this case, mobile vehicle is an underwater vehicle. And here the manipulator is attached to a drone, right? Multiple solutions for a vehicle manipulator, right? So a vehicle manipulator basically will have a dexterity of a manipulator. It can reach a position or can grasp any obstacle through multiple ways, and it can also have unlimited workspace like a mobile robot. And we have seen, the cases of a legged locomotion, different solutions where we can use legged locomotion. And the problem with legged locomotion is that, like, they are highly versatile. Like, they can use for outdoor applications, but they require, they consume a lot more energy than compared with wheel locomotion. They are highly complex. They are inherently unstable. They consume a lot of power, right? And we have also seen covered the advantages and disadvantages of legged locomotions over other systems. Uh, they basically leave less footprint on this environment. Effect on the environment is actually quite less compared to a wheel robot, right? And compared to a mobile robot, they can achieve higher velocities. They can run, they can sprint. And mobile robot, their speed will be limited if the environment is uneven. And again, we have seen different how the robots are employed on healthcare sectors. There are multiple classification of healthcare robots. We can deploy them on surgeries, exoskeleton. We can deploy them on rehabilitation. We can deploy them on care and hospital care and services. And we have also seen multiple objectives or multiple advantages of medical robots. They have much higher accuracy, geometrical accuracy compared with a surgeon. Like human hand cannot, operate with high precision in micron level scale. But if you scale it down to a robot manipulator, it can basically operate it with much higher accuracy than a human hand. And similarly, you can also go through all the other advantages of medical robots. And we also have limitations of medical robots. Because one of them is limited haptic sensing. Because like a human hand can feel whatever we are, the hand is actually touching or what it is subjected to. But that level of feedback cannot be obtained from a medical robot. And we have also seen, different control paradigms for, kind of healthcare robots, whether it's pre-programmed or semi-autonomous, where, the desired behavior is actually specified by the surgeon, and the robot will, fill the gaps in between, and it will communicate its planned program to the surgeon. And once it obtains surgeon's concurrence, it will execute the task on its own, right? But it's not fully independent. For every program it is executing, it needs the surgeon's concurrence. So that makes it semi-autonomous. And in case of a teleoperator control, the surgeon will control a surgical robot or a slave robot through a master robot. Right? It can have a master device, or the surgeon actually can control it using voice control. But each and every operation of the robot will be fully controlled by the surgeon. That is what we call as teleoperator control. And the third being hands-on compliant control. So this being the surgeon grasps the surgical tool held by the robot or a control handle on the robot's end effector. The force sensor senses the direction that the surgeon wishes to move the tool, and the computer moves the robot to comply. For example, if the tool is actually too heavy for the surgeon to lift on its own, the robot can support the tool, and based on the movements of the surgeon, the robot can accurately position the robot based on the surgeon's desire, right? And from there, the surgeon can actually do the fine manipulations. So that is about hands-on control. Yeah, and a similar question, a typical question from week 8 that you can expect is, in a system a large number of homogeneous robot executes their tasks with only uh, about their minimal knowledge about other robot team members. So this is a problem from multi-robot systems, and as you know, it deals with homogeneous robots, and each and every member of this homogeneous system has minimal knowledge about their teammates. That is a feature of this collective swarm systems. Yeah. So yeah, that is about it. Basically, the intention of this session was to provide a summary of all the topics that we have covered from week 1 to week 8. So yeah, so this will be the end of the live sessions for this course, ME uh, NOC24 ME67. So yeah, with that I'll stop wind up this session. Thank you.